It's okay. I'll do it again in a little bit. All right. So take a look at this one. Find me my zeros and my multiplicity. Oh, I should switch back to that one. There you go. So we have x equals 6, and that's a multiplicity of 2. X equals -8 with a multiplicity of 3. And x equals -5 with a multiplicity of 3. Neither of the problems I did, but if there was, say, instead of that 2 there, say it was 2x, you would also have to look at that one, and you have x as 0, would be one of your zeros. So since there was no exponent in that 2, that's why I didn't have to worry about the 2. You're only dealing with factors that have exponents or variables in them. And if we look at the graph for this one, click those first. It's like we were talking a minute ago. You can see how the multiplicities of 3, the odd ones, go through at -8 and -5. And then the multiplicity of 2, the 6, touches and turns around. Okay?
Does that go for even?
Yeah, so any even multiplicity or exponent in that respect is going to have that term. Any odd one will have it, it'll cross through. So typically if it's 1, you don't think about it, it's going to cross through that point because it's an odd number. So yeah, 3, 5, 7, any of the odd numbers, it's always going to go through. So it's kind of hard for you to tell, like I said, if it's going to be more than the 1 or the 2, because it doesn't really tell you much in the problem. You'll just have to look at the actual problem for it. But it gives you an idea of like, okay, if it's going to hit, I know I have to do it multiple times, so do it at least twice. So, all right. Questions with those? We will do a couple complex number ones in a little bit. Speaking of complex numbers. All right. How much do you guys know about complex numbers, other than the fact that they just exist? Okay, so yes, that's actually the first thing we're going to talk about is the eyes have a pattern to them, okay, that kind of repeat and can help you get rid of things. So remember, I is equal to the square root of -1. Okay, so no matter which number I have in my square root, if it's negative, I can pull out a square root of a -1. And then the number just exists and now it's positive. I would do my regular square root rules with it. So the I is always going to be the square root of -1. Now, if I did I squared, if I do a square root and a square, what happens to those two things? They cancel each other out. So that's -1. So I squared equals -1. If I have I to the third, remember exponents are just addition of the other numbers, right? So I to the third is really the multiplication of I and I squared. So it's -I because it's -1 times the square root of -1, which is I. So it's -I. I to the fourth would be I squared times I squared, right? -1 times -1 is 1. And then it repeats. So if I wanted you to find me I of 95, you just take the 95th power and divide it by 4. Somebody do it real quick for me. All right. All we care about is the decimal. So it's 0.75, right? That's the third one. So that's negative I. Okay. So since that's 3/4, it's the third one. So I to the 95 is negative I. Okay, so you can figure out basically any i's in that respect. For the most part, you rarely ever deal with i's past I squared. Okay? Yes.
Now, question about the negative square root. It was like -4, -9 would still be just I, just like negative square root of 1.
No. So if it was the square root of -9, that would be the square root of -1 times the square root of 9, which would be 3i. So because remember, any numbers you can break apart. So basically, if it's a negative, I can take out the square root of -1, and then I just have the number that I treat like a normal square root. So that's why I will always be -1, because I've always pulled that out. Okay. All right. Like I said, you're rarely ever going to deal with anything past I squared, because when you're multiplying, and I squared gets rid of it. So after that point, it's always back down to either 1 or the 2. So if we're going to multiply these,
does it not work if the exponent is odd or even?
So if I said that it was I squared or I to the third, like inside of it, I would have changed it immediately before I even did this problem, this next step. Or if it was I to the fourth, I would have just changed it to 1 and not worried about it. So that's what I'm saying. Like, you're rarely ever going to see that. You're going to see them like this because these are known as conjugate pairs, and conjugate pairs get rid of things. Remember, when you're multiplying conjugate pairs, the middle term cancels itself out. That's what we want. Okay? So this is where you're typically going to see it, is like that type of thing. Conjugate pair means basically the middle signs are different, but everything else is the exact same. So let's multiply these and see what happens. You treat I just like a variable when you're multiplying it and doing the FOIL out. All right, so treat I just like it was an X, and in the next step, we'll deal with it as an I. So X times X is X times -2i is -2ix plus 2ix. And then 2i times -2i is -4i squared. So these two terms right here, there's a negative and positive version, same thing, they're gone. I squared is -1. So this becomes x squared plus 4. Okay. Whenever you do a conjugate pair, there should be no i's left. Okay? Because the conjugate pair's concept is to get rid of the I. Because typically when you see a polynomial, you are not going to see an I in that polynomial. All right? You're going to see it as just regular whole numbers or integers or fractions and stuff like that. You're not going to see a complex number inside of a polynomial. However, we know that complex numbers can exist in them. It's because there's always a pair of them. One positive, one negative. So in this case, my zeros would have been x equals -2i and x equals +2i. Those would have been my two complex zeros. Same thing, just opposite. So you could literally just say it's x plus or minus 2i is the two factors for it. You're always going to have that when you're looking at complex numbers. Okay? You'll never have just one. You'll always have pairs of it. So you can have 2, you can have 4, you can have 8, but it'll always show up in pairs. All right, questions with that? All right. Before we do a complex one, I think it's the next one. Yes, it is. Let's do one with regular numbers first. So this one, they give you the zeros and they want you to find the polynomial. So this is kind of like opposite of what we typically were doing, where you're given the polynomial and you're looking for zeros. I wouldn't have normally done this topic, but I show it before I do the complex one so you have an idea of how to actually write them. You do not have to multiply these out once you get them. You can literally leave it in factored form in Alex. Okay? It actually says leave in factored form. So one of my zeros is 8 and it has a multiplicity of 2. So then my fraction, my parenthesis is going to be what? X minus 8, because it's the opposite of it, right? So x minus 8 and the squared, because it's a multiplicity of 2. The minus 4 is going to be x plus 4. And that would be my answer. Okay.
Oh,
Yeah.
yeah.
So yeah, so when you're looking at trying to figure out if it's a degree of 3, you just add the exponents together. So 2 plus 1 is 3. When you're looking at a factored form, you should have 3 sets of parentheses, and the square just means there's 2 of them. When you're only dealing with whole or real numbers, they're always going to have to either give them all to you or it's going to be a combination of multiplicity. When you're dealing with complex numbers, they won't, and that's where it's going to come in the next one I'm going to show you. All right, so here's a one with a complex number in it. It's got the negative 3 plus I. And it wants a degree of 3. So that means I need 3 zeros. I've got 1 with the x minus 2. So that's x plus 2. Now this one, I have to have the plus and the minus version of it. So I have x plus negative 3 plus I. And then x minus negative 3 plus I. So remember our conjugate pairs. The last one we had was x plus 2i and x minus 2i, right? Same concept. Plus plus, and those are my complex numbers. Okay? I'm just going to keep them in the parentheses at that point. In this one, you do need to factor it out. I mean, FOIL it out, sorry. Because you do not want complex numbers in your final answer. So, first question, everybody understand where I got to that point before I FOIL these out? Okay. And since it says a degree of 3, I have 3 parentheses. Okay, so I know I have a degree of 3. Just real quick so I can FOIL it out. All right, so the first one, the x minus 2 is, or x plus 2 is simple. But let's deal with the other one. So I have x minus or plus negative 3 plus I and x minus negative 3 plus I. Notice I put the negative 3 plus I in parentheses because it's going to be really easy to screw up your signs if you don't. Okay. So this first one, first thing I'm going to do now, I'm going to get rid of my parentheses. So I have x minus 3 plus I. And this one I have x plus 3 minus I. Remember, you have to distribute the signs. Now we flip. Doesn't matter if there's 2 or 3 of them. Process still stays the same. You just have to do more. So x times x, x squared, x times 3, 3x, x times negative I, negative xi, negative 3 times x is negative 3x. Negative 3 times 3 is negative 9. Negative 3 times I is negative 3i. Oh, is it positive? Wait. Oh, you're right. Sorry, I was good catch on signs. I'd have caught it in the next one when I said it couldn't cancel out. I times x, positive xi, I times 3. Wait. Hold on. So that's positive 3i. And that positive. Wait, hold on. Did I screw up my sign somewhere? My eyes cancel out. Why aren't my eyes canceling out? That's not the.
I just thought you switched the sign in the equation, so rather than it being negative, a sign with your equation.
It should have.
But if you just switch it to I minus.
Because those are different.
I mean,
Hold on. All good points. I'm just trying to figure out where I messed up. It's one of those things like I know I messed up somewhere. It's like it's just not popping out at me. It's always the little things. Huh, man. And of course, now the internet decides to go slow on me. Oh. All right. Who said I switched the signs wrong? I know. You were. I was gonna say, who said I switched the signs wrong? You switch it inside, not outside.
I was like flipping down to
Yeah.
see if that's wrong.
No. All right. So this is where one extra step that I didn't say that we just always do is very important. What is the actual format of the parentheses? It's always x minus the thing. So it's x like minus a, x minus b. So like that x plus 2 is really x minus negative 2. Okay? Which means this is really x minus negative 3 plus I. And then x minus the conjugate, which is negative 3 minus I. Always minus. Well, yeah, it's going to end up changing. No, you don't have to change the number in front. It's just the I. Because the conjugate's just changing that extra piece. So this now becomes x plus 3 plus I, x plus 3 minus I. Which now we could FOIL out and get rid of the 3's. So this is one of those things that I don't typically do. Like there's a lot of teachers will sit there and have the nice PowerPoints all done up with all the steps, and they'll just click through and go through. You'll notice I don't do that. I literally do everything live in front of you. This is the first time I saw this problem. Like, I haven't played around with these problems and figured out all the answers and stuff before. For two reasons. One, because I make mistakes just like everybody else does. But the second reason is one of the most important things that you guys can learn is how to spot a mistake. Okay? Because no matter how well you guys do, you're going to mess up at some point. So it's being able to look through the stuff and say, okay, where did I screw up? So that you don't make those mistakes later on. So, and also I don't care if I make a mistake. It's like, we learn from them. Like that. It's like, that's a simple mistake that easily could have been made. And I did it. But when I got through the stuff, I know all my eyes are supposed to be gone. They weren't going away. So instead of just continuing through the problem to get the answer and go, oh, I'm done, because you didn't realize that piece, now it's like, okay, I know I made a mistake. Where did I make my mistake? Let's go find that out. All right. That's an important concept that unfortunately is lost in math because we always keep saying you have to have the right answer. You have to have the right answer. Sometimes getting the wrong answer and figuring out why is actually more useful in learning things. So, big, long way of saying I screw up. It happens. All right. I just use it as teaching moments instead of saying, whoops. So we have x squared plus 3x minus xi. Now we do the 3. We have 3x again plus 9 minus 3i plus xi plus 3i and then minus I squared. I'm running out of also notice that a lot of times people will sit there and write them all in one long line. That can work. Notice how I'm lining things up so I know which ones have to go together. Because again, when you write them in one long line, now you have 9 things that you're looking through. It's really easy to mess things up or mix the sign up or not realize what you're looking at. By lining them up, it makes life a little bit simpler to deal with. So I have x squared plus 6x. Those are gone. Plus 9. Those are gone. And minus I squared is minus a negative 1. So what I have right now is x plus 2 times x squared plus 6x plus 8. Jesus. Okay. Signs aren't my deal today. 10. I'm going to do a lot of multiplication problems with side numbers later today. Because for some reason, they're just not working for me today. So that's fine. You can leave it like that, or you can multiply it out one more step to actually get rid of the x plus 2. But you just need to have one that does not have any complex numbers in them.
We have to do that. You would accept it. That,
I'd accept what I circled or the foiled version of that out. I would not accept this. I'd accept that version right there, or I'd accept the foiled version out. Yeah, you can multiply that out if you want. I just don't want to. There should be no i's in it, because in a polynomial you're not going to have any complex numbers. Right, which is why I said you didn't have to do that. All right. So we want to find our rational zeros for this one. So how did we say last class we were doing this? We are going to use synthetic division. But how are we going to figure out what we're going to cut out with synthetic division? Yeah, the rational number theorem. So remember, it's always over the factors. So actually, we don't even really need to look at the leading coefficient. We just need to look at the constant. And you just want to do plus or minus that in the graph. Because that's going to be the biggest and the smallest possible zero that you can have is -5 and 5. So I always go one more than that when I'm looking at a graph. So this is what my graph looks like. I just went from -6 to 6 because I know I'm not going to.
That's right, use the graph.
Yeah, I know I'm not going to have anything else outside of that. Yeah, we're not going to have to find them all. Although this one wouldn't be horrible. There's only 4 of them, but we're not going to have to find them all. So I know I have a -5 works. That's a fraction. That's a fraction, and I know a 1 works. Okay, so I'm now going to use synthetic division to take out the -5 and the 1. And then we can see what we have left to figure out where we're going to go from there. So I know x equals -5 and x equals 1. So let's do synthetic division. Yes. You don't have to change the signs. Oh, the screen didn't switch. Thank you. All right, so we'll do synthetic division. So we'll start with the -5. So 7, 27, -40, 1, and 5. I don't have anything missing, so I don't have to worry about that. 7, -35, -8, 40, 0, 1, -5, 0. Now remember, that has to come out what? 0. If it doesn't come out to be 0, you mess something up. So now we can take this and just do the 1 to it. Again, it comes out to be 0. So I'm good. So I'm now left with 7x squared minus x minus 1. Now we know from our graph that those are going to be fractions. They're going to be rational numbers. So, or irrational numbers. They could technically be. So at this point, it's a quadratic. I know I can't factor it, so do the quadratic formula. Even if it comes out to be 2 fractions, if you do the quadratic formula, it's not the end of the world. It's easier than trying to figure out a way to factor the problem out at this point. So I do the b squared minus 4ac. Remember, always do the discriminant first. -1 squared. I have 1 plus 28, which is the square root of 29. So I have 1 plus or minus the square root of 29 over 14. Are my other 2 zeros. And if you want to check and see if you did those right, you can easily, I'll let finish people finish writing before I swap on you. Just go into Desmos, and you can check those 2.
Are you gonna just accept 1 plus or minus 29 over 14, or do you want to?
No, that's fine. Yeah, that would be fine. Because those are the 2. So you can easily just throw those back into Desmos and check them. I would not accept negative 0.313. I want it as the 1 plus the square root of those things. So, all right. So that's easy way to check your work. Again, check your work. Like you have the options, you have the ability to do it. Use those things to check your work before you turn in your test. And before you, honestly, even in Alex, like before you hit submit, check it because it'll save you extra work. Okay. You're not going to catch every mistake, but sometimes you're going to catch those mistakes. Yes.
So when we do the test, find the zero.
Yep.
What if you want us to use a graph?
Yeah, you're going to do exactly like I just showed you. So yes, you're going to be allowed to use a graphing calculator or Desmos on your phone to do it. I said that as long as I don't walk around and I see people using Mathway and everything else to do things, then we're good. If I do, then people are going to have to buy graphing calculators and nobody's going to be happy. So let's not make that happen. Okay? Yes,
Go back.
absolutely. So yeah, you're going to use the graphing calculator to find the rational ones. We're using the rational zero theorem to figure out where I'm looking because I know nothing's going to be bigger or smaller than that. And then we can use that to narrow things down, and then we'll have the quadratic formula to do the quadratic.
If you don't have a calculator, you would work with.
Yeah, you could do P over Q for this one. Because you'd have 5 and 1 on the top and 7 and 1 on the bottom. So you'd have 5 over 7, 1 over 7, 5 over 1, and 1 over 1 would be the ones that you'd have, plus or minus those versions. So you'd still get the negative 5 and the 1 from it. So you just have to test more values. So, and when you're testing them, the only ones that would work are the ones that come out to be 0. The thing about it though is if you're going to test it that way, once you get a 0, don't go back to the beginning. Work with that now known number. So like if you start off at negative 5 because that's the smallest one you'd have, it works. So okay, we got the 0. Don't go back and do the 7, 27, negative 41, and 5 again. Use the 7, negative 8, 0, and 1 to work with that because you've already pulled something out of it. You want to try to simplify the problem down as much as possible. So you do the next one. You're doing them in order. The next one I think would be negative 1, which wouldn't work. And then so you go back to the 7, negative 8, 0, 1, do those. Okay, so always go back to the piece that you've simplified down. So you're always trying to get the problem down as simplified as possible. And then technically, once you get to a quadratic, you can always do the quadratic formula. All right, even if they all come out to be actual like integer numbers, you can still do the quadratic formula once you get down to a quadratic to figure out the last two. So this method is just nice to be able to try to simplify them down so we can do something else. Any other questions with this one? Okay. All right. This one gives you the two zeros. So I don't even have to graph it. They give me a couple of zeros for it. It's a fourth degree. I've got two zeros. I'm getting down to a quadratic. I'm good. So you don't necessarily have to graph this one. So do my synthetic division and break this one down. To the quadratic. And you don't have any, you don't need any zeros in this one, which is nice. So we have 4 zeros in this one. X is -3, X is 2. When you're writing down the zeros, don't forget to write those down. They are still zeros of the problem. And then we have X equals -2 plus or minus the square root of 5. So this is one of those ones where people always ask, do I have to simplify down the square root? You'll lose a point. It's like not simplifying down a square fraction. So like if it's 2/4 and you leave it as 2/4, you're probably gonna take off a point because you should have put 1/2. Same concept here. If you do it and simplify it wrong, I'm still only gonna take off the point. So it's not like it's the end of the world if you mess up simplifying it down. But it is something that you really do have to get better at, simplifying down those square roots. Because I'm dividing everything by 2.
Would it be 2/5?
No, because that's a multiplication. So it's -4/2, which is -2. And then 2 to the square root of 5 over 2. The 2's cancel out. I don't think I screwed up my signs in this one. If it comes out to be a complex number, which the next one I believe does, I'll say I do that one too. We're just going to pull out the I first of all on that. So, but everything else basically stays the same. All right. All right. Find my zeros for this one. On any topic where Alex says use the Alex graphing calculator, you can use Desmos. We're going to do a few of those in a few minutes. Yeah. Yeah.
So how would you know whether
Synthetic division will always be applicable in these situations. Because remember, the synthetic division always works with a linear function or a linear term when we're factoring it out. So since these, when we're factoring out just a single number, is always a linear term, always use synthetic division for it. So that's actually one of the reasons why we show synthetic division, because for like these situations, it's so much easier than trying to do a long division to break it down. And notice again, I just looked from -6 to 6. I just do one more just in case it crosses through like it does at 5. Because I just looked at that constant at the end. And it doesn't matter which one you do first, the answer will still come out to be the same. So if you did the 5 first instead of the -1, you'll still get the same answer at the end. Right? And then again, we're looking to make sure they come out to be zeros. That's the check to make sure that I did those steps correct. Yes, there's a possibility you mess up multiple things and it still comes out to be right. It's less likely though. And it's less likely that you're going to get two of them to work. Like you might get the first one to come out to be zero by making a mistake, but then if you do the next one, it's less likely that that one's going to come out to be zero too, because that means those numbers are wrong. So since they both come out to be zeros, pretty sure that you did that one correct. So now same thing. B squared minus 4ac. So I've got b squared minus 4 times 3 times 1. 4 minus 12 is negative 8. So we do the square root of negative 8, which will be 2i square root of 2. So the I takes care of the negative sign, and the square root of 8 is 2 square root of 2. Does everybody understand how I'm simplifying down the square roots? That was that factor tree that I did the last time, or just remember how to factor them down. Some people sit there and focus on like the perfect square. So like 8 is 4 times 2. So you can do the square root of 4 is 2, and then there's the 2 left over. That's one way to do it. I always like the factor trees. So, but the ones that show up a lot, at some point you're just going to remember the basic ones. 8 tends to show up a lot in these problems. Not yet, because I still have to do the last part of the actual quadratic formula. Yeah, so x equals, I have negative 2 plus or minus 2i squared root of 2 over 6. So x equals negative 1 plus or minus I square root of 2 over 3 would be the final answer. Remember, I do the discriminant and simplify that out as much as possible before I plug back into my quadratic formula, because then at that point you really only have one step to deal with, and that's just the simplification. Get into the habit of putting the I in front of the square root and not after the square root. Get into the habit of putting anything in front of a square root instead of after the square root, because it's really easy to screw up where the square root ends. So yeah, just get into the habit of putting that square root first, or the numbers first. Yeah.
It was like the I to the root of 2. Well, no. 5i. Would you leave it over the 6?
Yeah, I wouldn't have simplified it at that point. Yeah, I wouldn't have simplified it at that point. And actually, even if it was 3i to the square root of 2, you could have simplified it, but it would have been 2 separate fractions. So at that point, I probably would have just left it as is. So, yes. It's negative b. The quadratic formula is negative b plus or minus the square root of. So b is 2 in this case, so it's negative 2. Good, we're getting questioned all my negative signs now. So in this case, we have 2 real numbers and 2 complex numbers. I always do the discriminant first. I always do the b squared minus 4ac first, because if you look at the whole quadratic formula, that's the most complicated part of it. So if I do that first and simplify that down, when I actually write the actual quadratic formula, all I'm literally doing is plugging that in, and it's just negative b over 2n. So it makes it a lot simpler to work with. What I typically see is when people write out the whole quadratic formula, they plug all the numbers in, they're more likely to make mistakes because there's so many numbers there to deal with. So that's why I always focus on the discriminant first. And the other nice thing is that if the question's asking for real numbers and you do the discriminant first and it comes out to be a complex number, you're done. You don't even have to worry about the rest of the part because you know you don't have any more real numbers. So All right. So the next few topics we're going to look at are going to be word problems, really. So we're kind of going to move on from finding zeros. Those will always be important. We're going to use those quite a few things, different things later on, but there are other parts of polynomials that are also important to deal with. We have the local mins and maxes and behavior and those type of things. So we're going to move into some local mins and maxes and look at the couple word problems that Alex uses quite often. So this one actually is really straightforward and simple. It says use the Alex graphing calculator. They don't want you to do this out by hand. Normally when they do this, they actually will take an estimated answer anyway. The Alex calculator is always going to round it anyway. I think the Alex calculator rounds to 2 decimal places though. So let me just make sure. It's 10. Yeah, I'm wondering if it looks at, for 2 numbers or 3 numbers. Yeah, it's a bit. They want it rounded to the nearest hundredth, and the Alex calculator actually gives you out the whole decimal. So when we're doing a problem like this, you're just going to go to Desmos and put it in. I know I'm not switching over yet because I need the actual problem. And this one's asking for where there's a local minimum. All right, so here's my graph. If you didn't finish writing the problem down, there's the problem. And we're looking for local minimum. So how many local minimums does this problem have? 2. Remember, there's a difference between local minimum and absolute minimum. If it asks for absolute minimum, there would only be 1. And this would be it. Since it's asking for the local minimums, I have 2 of them. Those are the 2 local points. So anytime it dips and turns and goes back up, those are local minimums. So I have 2 in this case. So we can round. So you get negative 2.10, negative 5.104. So in this situation, that's all it's asking you to do. And Desmos is a lot easier to use than the Alex graphing calculator. Alex graphing calculator is very similar to the TI calculator, where you have to put in and then tell it what ranges to look for, and then it'll find your minimum. This one, it's just there, just click and get your answer. So again, just remember to round to 2 decimal places.
5.1.
So your answer would be negative 2.10 and negative 5.10, and then 0.87 and 0.88. Those would be the 2 points. If it asks you to round to the nearest hundredth, I don't know if Alex is as picky at this as they should be. If it asks you to round to the nearest hundredth and the hundredth is a 0 because you rounded to it, you have to put the 0. It is? Okay. Because that represents that there's other stuff there, but you're rounding to that. So, okay. And that can be extremely picky if depending on what you're doing later on in engineering or your science and those type of things, those numbers actually become very important. So keep those little things in mind. So don't put negative 2.1 and negative 5.1. Put the zeros there. Simple enough? Okay. The reason for this topic is this topic. All right. So that topic's really easy because it really wanted to get you to practice to find local mins and maxes on the graphing calculator. Because this problem now requires you to come up with a word problem to find an answer for using the graphing calculator. So it says a rectangular piece of cardboard with a perimeter of 17 inches. 3 parallel and equally spaced creases are made. The cardboard is then folded along the creases to make a rectangular box with open ends. Letting X represent the distance between the creases. Use the Alex graphic calculator to find the value of X that maximizes the volume enclosed by this box. Okay. So, how do I find volume of a box? Start with that part. Volume is length times width times height. Okay. So, I now need to find my length, my width, and my height. They gave you a length and width in the problem. Those are X's. Okay. What's the height?
Why?
They got to be in terms of X's. What else have they given you in this problem that we haven't used yet? 17. So the perimeter of this is 17. Okay? Huh? Why 8x? Correct. I have 4x's here. I would also have 4x's here. So if I'm looking for this side here, okay? So actually, you were almost right. You missed one thing. Because, so if this is my height here, that's also my height, right? So it's going to be 17 minus 8x divided by 2. Okay. Now, I will tell you right now, that's the hardest part of this topic. Everything after this point is a piece of cake. All right. It's literally trying to figure out how we set up the problem. And as crazy as it sounds, this right here, actually, I've used. I had to make boxes to ship out because I do 3D printed dragons. I literally had to make boxes to ship out dragons. The post office uses what's known as like the girth, which is a round, to calculate things to figure out how much it's going to cost you to send it. So I needed to maximize the volume of my box to put as much in it and minimize that other number. So I actually had to do this in real life. It's not just a math problem. So is everybody going to do it? No, but there are situations where these things come up. You go to the movie theater when you're looking at popcorn buckets and things like that. They actually want to do the opposite. They want to make it look as big as possible with the smallest volume as possible. Because then they give you less popcorn, but you think you're getting a lot. So these things actually do come up into play when you're looking at maximization or minimization of volumes. We now have our problem. All it's asking for is what is the value of X that's going to maximize it. So I would then go to Desmos and graph this. So X, I'm going to switch over in a second. I just got to finish the problem. When we graph it, I literally just type in length times width times height. I didn't multiply, I didn't do any of the crazy stuff. Type that right in. And the X that's going to maximize my volume is 1.417.
That's to be equal to 0.417.
So X would be equal to 1. Well, I think they want the hundreds. Yeah, 2 decimal places. So 1.41 or 1.42, sorry. Running. And now won't work there. It will work here. So the Desmos scientific calculator actually has a really cool feature, which most people don't use very often. So in Desmos, the scientific calculator, you can type in a formula and then put in what you want x to be. What was it, x.142, right? Yep. And then you can put what x is, and it gives you the answer. It plugs the values in for you. So you don't necessarily have to type the thing in, put the 1.42 in, just type the formulas. And if you had already done it in Desmos, you can literally copy and paste it into the scientific calculator. So you don't have to retype it. And then just put x equals there. This actually works for any formula. So, like, let's see if we had formula for, if we did 2 pi r and we did pi r squared. Because we were looking for circles. And r equals 4. It'll give you the answer. It'll plug them all in. So more complicated quadratic formula, you can do it here. The problem is doing like quadratic formulas, it will not give you as a exact answer with the square roots. It'll give you with the decimals. But if you're looking at estimating things or rounding things and stuff like that, this works perfectly fine for those type of things. So using this can help. So the answer to this question was 1.42 inches. And then my volume was 5.69 cubic inches. Because it wanted both. That was I plugged back in the X to find the volume. So that's what we just did here. I plugged in those. That. I just plugged the 1.42 and it automatically did it there to get the volume. So you don't necessarily have to sit there and go through and calculate it out yourself, or replace all the X's with the 1.42 and possibly forget a parenthesis or something like that, or it'll just do it for you. Yeah. Yes. So here's my suggestion. You have a phone, I would download 2 apps. I would download the Desmos graphing app, and I would download the Desmos scientific app. Those 2. And you'll have them both. Do you have to? No, you can go to the website and work the same way. But having the app on your phone is kind of nice because if you don't have internet or anything else like that, it still works. So those 2 would be the apps that I would download. They're absolutely the best graphing calculator out right now, and it's free, unlike the $100 TI calculators. So, yep, there's 2 different apps. And unfortunately, I don't think they both say Desmos. I know when you put the app on it, I don't think it says Desmos on the front. What's up? I'm literally in the middle of class, so that's why I answered the phone, because I figured it was an emergency. Okay. Okay, bye. If they call me in the middle of class, I'm going to assume something's wrong. But no, she just missed the time.
Can you give them instructions not to, and that's what it is.
Well, they know that. She literally screwed up the time. She thought I was done already. All right. Let's see. Let's do one. Let me do one more of those, because the word problems can be a pain in the butt. So let's do one more word problem. Nobody likes word problems, but like I say, they actually are where you use some of this stuff. All right. Maximize my volume. That's a 4. If you can't read the numbers, that's a 4, and that's a 2. And all the letters inside are X's. This topic will always be volume, so it should. They're basically going to be using boxes like these. What's the length? Oh, that's fine. I made that my width, but so 2 minus 2x. And then the length would be 4 minus 2x. And my height would be x. So graph and Desmos. And that's what you end up getting. If you think about it, another things that you want to use to check, you know your x can't be anything bigger than 1. Because if x is bigger than 1, one whole side of the thing is gone, right? So you know you're really looking between 0 and 1 for the value. So that's one of those things, like when you type it in, if you get something that doesn't meet that expectation, go back and check what you did. So in this case, my x is going to be 0.42. So then my volume, Desmos, and we get 1.54 cubic inches and inches. So while they seem extremely complicated, once you get your pieces for length, width, and height, everything after that's actually pretty simple. So it's not like you're sitting there trying to do this all out by hand. So once you get those three things, that's the hardest part. And they will always give you a picture for these. So use the picture to your advantage and try to help out. I think the perimeter ones are harder than this one just because you might forget the other side or forget to divide by 2, those type of things. But these boxes are pretty straightforward. Yeah.
Putting it into the graph as y equals 4 minus 2x times 3 minus.
I didn't put the Y,
Oh,
but you don't. You don't necessarily have to put the Y. Desmos will assume it's Y equals, but on that you don't have to either. So any of the graphic calculators will assume it's Y equals. Unless if you put Y, like when we get to other things, like if you change these to Y's here, it expects you to put X equals. So, we had ones like that when we did the inverses. So it will assume Y. It will assume it's Y equals. It won't assume anything else. All right. Almost done. 2 more things. Did your college algebra or whatever class you took before this talk about end behavior?
Yeah.
Okay. How'd they explain it?
They did it with the degree, something like that, and you have to like say whether it's continued, going through, or going. And it was like, what they did was they usually gave us a graph, and then they would like circle points, and then it'd be like explain.
Gotcha. All right. You need 2 pieces of information: your leading coefficient and your degree. Okay. Your leading coefficient will always tell you what the right side of the graph does. All right. So the leading coefficient will tell you if your right side goes up or goes down. The leading coefficient, if it's positive, right side goes to infinity. If it's negative, the right side goes to negative infinity. Okay? So the leading coefficient will always tell you that part. The degree helps you figure out what the left side does. If it's even, the left is the same as the right. If it's odd, the left is opposite the right. And that's it. So find your leading coefficient first. That tells you what the right side does. And then use the degree to figure out what the left side does. And there's not a million steps in there. So even if they ask you, well, what does the left side do? Just do the same thing. It's not that hard to. All right. Everybody got that written down somewhere? Left is opposite of the right. So odd is the left is opposite of the right. So if the right went up, the left went down. The right went down, the left went up. Yep, this is end behavior.
Professor like gave us behavior.
Yeah, graphs are simple. Like if they give you a graph, you literally are just looking at the end and the left and the right. The other thing that can come into this when we start to look at horizontal asymptotes and those things, the as it goes out, it might not go to infinity. It'll go to a different value, but those aren't polynomials. Those are when we start talking about rational functions and stuff like that, which we will talk about next class. So we'll get into that.
And I remember they would do like piecewise equation.
You can have some crazy stuff in there. So this one actually is purely polynomial, purely end behavior. She's like, I have no clue. So let's look at the first one. And I don't even care what the numbers are. The leading coefficient in this case is negative, and the degree is odd. So that means the leading coefficient is negative. So on the right side, it's doing what? Going down or going up?
Down.
Down. So that means it's falling to the right. And since it's odd, it's doing the opposite. So it's rising to the left. So that means it's that one. Let's look at B. My leading coefficient is negative and my degree is even. So the right is falling, even, so they both fall. What about this one? This topic will always give you one that looks like this. Okay? The only thing that makes it a little more complicated is trying to figure out what the degree is in the leading coefficient. So in this case, my leading coefficient, it's just the numbers in front times each other. So in this case, it's 3, which is positive. And my degree is just the sum of the exponents. So in this case, it's 4, so my degree is even. So my right side's going up, and since it's even, that means my left side's also going up. So it rises to the left and rises to the right. Pretty simple, straightforward. Yeah, like I said, if I gave you a graph and you couldn't tell me what the left right side does, I'd hand you my glasses. Like, because that's literally, it's like, those are simple. The equations make it a little more complicated. Let's look at a graph. All right, so this is one of those topics that looks very complicated because it has a bunch of stuff that it wants from it. But again, a lot of things look more complicated than they are when you have no clue what they're talking about. So this one's going to give you a graph, which makes your life a little bit easier. It's going to ask you some information about it. So in this case, the first one's saying, over which intervals is the function decreasing? So we're looking at ones where the line's going down, basically. So in this situation, my line's going down a few places. It's going down here, 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 and here. Those are the 4 places it's going down, right? So that means it's going down from negative infinity to 7. It's going down from negative 5 to negative 2. It's going down from 3 to 5. Oh, sorry, is that 6? 3 to 6. And it's going down from 8 to infinity. So once you mark where they're going down, or if it was asking increasing, same concept. Mark them increasing and then mark off the intervals where it's doing that. All right. Are you trying to figure out the next question? Yeah, I know, they're so small in here. So this next one's asking for local minimums. So I have a minimum here, here, and here. So that's -7, -2, and 6. So -7, -2, and 6. What's the leading coefficient? It only asks the sign, positive or negative. Why? The right side's going down.
Could you find what the number is?
Not simply. Not easily. Could you? Probably, but you'd have to use the zeros and then use another point. And this one's a higher degree function, so it's going to be a little messy.
So
So
like we did.
not on something this complicated. You might have done quadratics with the x squared. You might have done a cubic. I don't think you would have done anything past a cubic though.
Oh, yeah, but I'm like, I'm pretty sure he had us like look at something like that, describe the end behavior, and then come up with the equation.
Yeah, we like.
Oh yeah, yeah. If the graph gave you the zeros, you could have easily come up with that and then used another point to find the a, which would have been your leading coefficient. Absolutely. But they would have had to have given you the zeros, or it'd have been a quadratic. Cubics are a little more complicated. They don't give you the zeros. Quadratic, you could have easily found the zeros with the end behavior and stuff like that. So it really depends on the type of graph they're going to give you and figure out. It does come up sometimes with modeling and things like that you do have to come up with a function for it. So that's not a horrible thing to know. Last question. What is the degree of this function? Okay, so it's odd. So we know that. So that means it can be 5, 7, or 9. Could it be any of those? So now the next question is we have to figure out. So there's another piece of information we can use to figure this out. The number of turns helps you figure that out. So in this case, I've got 1, 2, 3, 4, 5. I got 6 turns. It's always one more than the number of turns is the lowest degree it could possibly be. So in this case, my degree could be a 7 or a 9. So like you think about a quadratic, it has 1 turn. So it could be, that's where the 2 comes from. It's always one more than that. A cubic has at most 2 turns. It could have no turns. And a cubic, it could be just basically a flat space with no curves. But the most it would have would be 2. So you add 1 to it, that's where you get the 3. So the first thing you can figure out is what it is even or odd. And then you can use the number of turns to figure out the next step of that. So in this case, it's going to be a 7 or a 9. All right. Any other questions? We are moving our way through chapter 4. I've done probably about 30-something topics in chapter 4 already. Between last class and this class, we will finish up the chapter 4 topics next week. So remember, the test is already online. So you can start working on that and continue to work on your topics.